value vector is always S times K size, where K is the horizon that you're looking at. This much you understood. Now my question is, you figured out how to compute the value of one policy. I came into this world trying to compute the optimal policy. So I pick up, again I'll do the same idea, which is somehow this policy was given by somebody, I computed its value. I can imagine I just made it up out of my mind. Okay, so for S1 with K to go, I'll use A1, etc. So I just basically decided some actions for each S and K combination. That's a policy. Now is this optimal or not? The way you could figure this out is dream up another policy. Thankfully, there are no dearth of policies because there is S power K times a number of policies. Right? So you can dream up until cows come home. And for each policy, you do this computation. And compare the two vectors. You see what I'm saying? And you will say one vector is better than the other vector if across the board it's either greater value or equal value than the other vector. That's a very reasonable way to define. You see what I'm saying? Now I'm giving you a second order brute force approach for computing the value, computing the optimal policy essentially. So first I gave you a brute force approach for computing the value of a policy, and I said this structure, you can do this much faster. Instead of empirical simulation, you can do this. Now I am saying, I now want to go from here to the optimal policy. The brute force approach would be, think up a policy, think up a pair of policies, check which wins, then think up next one, whoever is left in the end, that's the optimal policy by definition. So it would be a nice order S power Ka complexity. N factorial looks easy by comparison. Right? This is where we realize that optimal policy and optimal value have this nice connection. In fact, whatever we did earlier about V0s, V1s, etc., Vks, we can start doing it in terms of V star, which is the optimal value. And you can directly compute the optimal value function. It will be a little harder than just computing the value of a policy. As you saw, it will involve maxing over multiple actions that you can take from that state. But if you do that maxing, then you will get the value, optimal value of all the states. Once you get the optimal value of all the states, you know the policy. Okay? And to do that, essentially, now first let's actually see the following thing. Suppose I am at S1 and I have K stages to go. I have computed optimal Vk minus 1 star, Vk minus 1 star. Okay, it's not actually the star should be Vk minus 1 star. Then if x1 can do multiple actions, let's say A1, A2, A3, then I will pick the action AI that gives the best expected backup. So that's how you convert optimal value to the action. So you know that now. The question then is, how did I get the optimal value? And basically you saw that. I'm just going to walk you through this again, which is, this is the set of equations, and these are called the Bellman equations. That's by Bellman. This is called the dynamic programming. And what they basically are saying is, V, in fact, if you don't put a pi, then V is optimal. So I can also put V star, different notations for optimal. Okay. So in this particular case, optimal value with 0 steps to go of a state is still its reward. That's a good thing. You agree? Whether you're following a policy or not, if you're dying right now, then what you got in this state is the value of this state. Okay? Right? So, that's V0S is Rs. And then Vk of S is R of S plus, remember previously for value computation, what you did was you did something like this for the action that you are supposed to do in that state. Now you do this computation for each of the actions you can do, take the max over it. You see the difference? So in fact, if you look back at the value computation equation, it looks almost the same, except there is no max over A. So it's just a bunch of linear equations. In fact, it's the linear equations of the form that we all love, where linear equations is like of the type x plus y is this much and x minus y is this much, what is x and y. The linear equations, simultaneous linear equations of the form that we really love are of the type y is equal to this much. And x plus y is equal to this much. What is x? You already know, given y is this much, then you put that value into x plus y, and then you know the x value. And that's what is happening in computing the value of this particular policy. Right? Okay? So, and then you did this here, except now what we're doing is that linear computation is no longer available. You have to do maxing over all the A's. Maxing over all the A's. Go home. So if you max over A's, this is the advantage of sitting in the front. I'll tell you where to go if you sleep. So it's hard to come all the way back. So clearly the reward is higher for you outside, so you should do that. Anyway, then you're taking the max over all the actions that you can do, and once you figure this out, you essentially get the optimal value for the entire space, and then you convert it into the policy, as I said, which is the policy for S with k stages to go is the action A that gives the best backed up value. In one step look ahead. Just one step look ahead. Okay? This is basically the formal definition of a finite horizon value computation. If you understand this, if you can see this, and you are able to think this, then you're in good shape already. But if you don't see that it's connected, we'll just see that this is how it looks like essentially. So this is called the Bellman backup. The way we compute Bellman backup in this particular case is like again you have S1 to S4, and I have two actions, the red one and the yellow one. Okay? So I can see what the red one will get me. The red one will get me for state S, the red one will get me 0.7 times VTS1 plus 0.3 times VTS4. I'm computing the VT plus 1, horizon T plus 1, in terms of horizon T. The red one will get me this. The yellow one will get me this. There are two different actions. Which one will I pick? I'll take the one which is maximum. Right? So I take the maximum of that, and then I throw in my own immediate reward for being in this state. And that would be Vt plus 1s. That's it. Now, if this thing looks kind of confusing, look at it that way. It's just expect a max. I just made huge amount of additional terminology and threw in Bellman also into the equation, truly, and it looked different. You see what I'm saying? It's the same thing. You did this and expect a max. Okay? And so basically what we are saying is the values for the lowest nodes are just the reward values. And then you're doing expectation, maximization, expectation, maximization, expectation, maximization, until you find the value of a state. And you're doing it for every state. See this? So it's not surprising, it's the same thing. It's just one is left to right, one is right, left, one is this. Sometimes perspectives help, so I thought maybe I'll give you something. Okay. Okay. So then how does the value iteration look essentially? You start with V0, I have the V0 values. Using that, I'll get the V1. And then after V2, after that V3. That's it. Except I just droned on and on in that YouTube video for like 15 minutes to do this. Because if I don't do this, they'll say, I don't know, the numerics weren't done. Okay? Numerics are less important. If you understand how the problem is supposed to be done, you should be able to convert to numerics. Right? Any questions about this stuff? It's just simple, right? It's just you're doing maxing in the middle. The only difference is that if it is value computation for a given policy, it would have been solving of a simultaneous equations of a certain format, what I call the diagonal format, where you will basically you have simultaneous equations of type x equal to this much, y equal to this much, z equal to this much, and x1 plus x equal to this much, x2 plus y equal to this much, and so on. And since the first guy's values are known, the second guy's values can just be computed by substitution. You don't even have to do matrix inversion for this particular value computation. For policy value. But to compute the optimal policy and to compute the optimal value, you will have to do the maxing. That's not linear. Okay? So, of course, this will give you the values everywhere, and then you have to convert it into the policy. And as I said, if you are in this particular place, and if you are in this particular state, you could do either this action or this red action or the yellow action. You pick the action that is bringing back the best expected value. So in fact, you don't even have to do it as a separate level. As you are making one pass through this, you can remember the policy. Right? Because what happened was, you took this max. When you took this max, you knew which one gave the max. You could just remember that as the action for that state. That's just computer science. That's just pre-10 data structures. So you won't say it normally. If you do this whole thing and do it all over again, then that's kind of wasted effort. Okay? Okay. Let's see if we can start this. Okay. So here is a bunch of facts about value iteration. What we did, by the way, this idea is called dynamic programming. How many of you have taken algorithms courses? Haven't you heard dynamic programming there? This is dynamic programming. In fact, dynamic programming essentially says keep the intermediate reserves, because you don't have to recompute them again. And it would be useful when the optimal solution has what's called optimal substructure. If the optimal solution has optimal substructure, then you can use dynamic programming. Here is the idea. Suppose you just went to the doctor and the doctor said, hey, I just did the calculations and you have 7 years to do. That's it. So your horizon is 7, my friend. Okay? So you know finite horizon MDP, so you quickly wasted some of your life and figured out the optimal policy for the rest of the 7 years. What to do in each state, in the first year, in the second year, in the third year, in fourth year, and fifth year, and sixth year, and seventh year. Then you went for a checkup back into the doctor and said, hey, actually I made a mistake. Right? You only live for 6 years. It's fine. I know what to do if I live for 7 years. I take the part of the policy for 6 years. That would be the optimal policy. Everything is coming up Milhouse. Those of you who know the difference. Okay? Then another day again, somebody else, your friend goes to in the same situation, goes to the doctor. He says, oh, I made a mistake, but it's good for you. In fact, you live for 8 years. You don't have to recompute the entire policy. You know the optimal value up to 7 years. You compute the optimal value for the 8th year. You compute what to do in that 8th year, and then follow the rest of the life. If you can do this, then the optimal solution has what's called the optimal substructure policy, optimal substructure property. In fact, everything we have seen till now has optimal substructure property. A-star search has optimal substructure property. In fact, A-star search does dynamic programming. Okay? And this guy, Bellman, basically came up with the name dynamic programming. And there's a story, somebody asked him, why the heck did you come up with this name dynamic programming? And he said, military was supporting my research, and I felt that they would feel kind of unhappy if I tell them I'm sort of working on work quotation processes. So whereas it would look more sophisticated if I say something around programming. So it's dynamic programming. It really, just like uniform cast search, which has no connection to reality in terms of the word and the meaning, dynamic programming, I don't know what the heck is dynamic programming here. It's like, why am I called Rob? Why is this called dynamic programming? It's just called. So if you're trying to figure out what part of it is dynamic, you're screwed. Because essentially you made up a name. The real part is its optimal substructure. That exists. Yes, sir.
For this, would all the calculations be done beforehand? So, like, would maybe that improve the speed at runtime because everything is already pre-programmed?
No. So in much of this stuff, actually, all of this is you're computing the policy up front, and you just use the policy during runtime. The version of it that's online is that expectemax version that I showed you at the end of the game trees. That in essence is using Bellman principle. You see what I'm saying? It just starts from wherever you are and goes a few stages lower, as against actually taking into account exactly what the horizon is. Okay? So you can spend all the time for computing the policy and value up front and just use it during the, yes?
So, can you use this for infinite horizon?
Yeah, we'll see that in a minute. Okay. So this is that's how that dynamic programming is used. It's because of finite horizon, the policy is actually non-stationary. That means the value, the action you're supposed to do in any given state changes based on how many steps you have left. Okay? And the computational complexity is, the worst is, of course, the worst idea that we had was O S power K8, right? Number of states power K times number of actions. Okay? Instead, it's actually only O times T is K. Basically, T is the horizon K. K times A times S squared. That's it. So, these two guys, instead of being in the superscript, are just friends next to S squared. Huge improvement in complexity. Huge improvement. Right? So it's only polynomial in the number of states. Now is this good? Well, it depends. It's better than this. Right? The one way you can show your algorithm is better is to come up with a dumb algorithm first. And say, look, with respect to that, this is a better improvement. And most bosses won't know the difference, so they'll say, yeah, wow, okay. So you earned your money for this year. Okay. So this is a summary of finite horizon, and basically what I want to do now in the next 15 minutes is infinite horizon policies. infinite horizon and diffusion policies. Infinite horizon is just finite horizon, but much bigger horizon. Right? In fact, I would argue that really infinite horizon does exactly this. The structure looks exactly like this. The difference is in the finite horizon, the intermediate results have physical significance. They are the values for k stages to go. In the infinite horizon case, they are just the kth iteration values. Why? Because two issues. First of all, you know that in the case of infinite horizon, as I already discussed last class, policy has to be stationary. It has to be. Because even if you live for 25 years, you still have infinite amount of time to go. You always have infinite amount of time to go if you have infinite horizon. Which means the policy has to be stationary. It can't possibly differentiate between V1, V2, V3, etc. Right? So then what that means is these computations of the intermediate values, they are just programs, internal approximation of what the real value is. There's only V, S1, S2, S3, etc. of Sk. And this is your first approximation. The value of a state, the first approximation is just its reward. The second approximation is this. The third approximation is this. The fourth approximation is this. The fifth approximation is this. When do I stop? Normally, if this is actually true, that these are approximations to the same thing, then as I keep going, the difference between these two vectors will become 0. Because after some number of iterations, this computation has to reach a fixed point, what's called fixed point. That means Vk plus 1 and Vk would be extremely close to each other. It should be 0, but there is no such thing as 0 in real numbers. You never check for 0. Instead, you say Vk plus 1 minus Vk. That will give you a vector of residuals. Take the max of that, max value of that, and say that should be less than, that should be close to, that should be less than or equal to epsilon. Do you understand what I just said? You take two vectors, Vk and Vk plus 1 and Vk, take the minus, you know how to do vector subtraction. You get another vector possibly of small negatives and positive numbers. You take the max of those. Okay? Basically, actually, you have to take the magnitude max. Sign doesn't matter. And that magnitude should be less than epsilon. Where epsilon is the threshold you set as the placeholder for 0. Because real numbers basically never become 0 in subtraction. You guys see this? So, if you have a finite horizon value function that you already written, you can just say, yeah, it's also the same thing that works for infinite horizon. Whoever is asking, can it be used for infinite horizon? Yes, it can be used for infinite horizon. You just throw in an epsilon and stop the terminate when Vk plus 1 minus Vk is less than epsilon. Looks good. Everything seems all done. Once again, we seem to be kind of Milhouse. How many of you know the reference? Everything is coming up Milhouse. Okay, rest of you should see it. Okay, it may be on the exam. You never know. Okay. So, for the infinite horizon MVP, the good news is that the policy must be stationary. You agree, right? It cannot be non-stationary. It just cannot be non-stationary. It has to be stationary. Which means there are only a power s policies instead of a power k times s or t times s policies. By the way, just so you won't get confused, in all the slides, t is used both to say the number of stages and also t of s, a, s dash, the transition function. So that's why when I'm saying it, I'm trying to call this k. Okay? Anyway, so that's just a minor thing. So the idea of value iteration, just run the finite horizon algorithm. Just run it. Except now each iteration is just an iteration, no connection to horizon. If there were to be unique optimal value function, if there were to be, this requires an actual theorem. We will get to that next class. In fact, that's the real reason why, in fact, not even Bellman, there's a guy called Howard who proved, I'm sorry, Ron Howard, who proved that, in fact, there will be a fixed point. And in fact, what is happening in each of these stages is you're taking this entire value vector, you call this operation a Bellman operation. And you get a new value vector. So basically you can think of this to be B of V0, I'm sorry, you can think of V1 to be B of V0. And similarly, V2 to be B of V0. Where B is the name for this entire operation. That's called the Bellman update. And the beauty of the Bellman update is that it has this property called the contraction property. And you can show that if you have two vectors, V1 and V2, you apply Bellman update to the difference. I'm sorry, you have two vectors, V1 and V2, then V1 minus V2, and you compare that to BV1 minus BV2. Okay, this would be smaller. That means the vectors after Bellman update come closer. That's the contraction property. Now if one of these values is V star, which is the optimal value function, then B of V star should be V star. Because if there is to be a fixed point, then you apply the update at the fixed point, then you should get the fixed point back. So if you do the same thing with V2 being V star, then you see that essentially what the Bellman updates are doing is each of these additional vectors are coming closer and closer and closer to V star, which is what we hope will happen. I will go through this again, but that's the general idea of what happens as to why Bellman update actually reaches a fixed point. You didn't need this kind of a proof for finite horizon, because there's only finite number of stages. If there are infinities and you are just saying, there's a program, we just run it, who told you that the program will ever end? Well, everything looks good. Everything looks really, really, really good. But for an immediate problem, this is the immediate problem. Why would you believe that any of this stuff? If you have infinite horizon, you have an infinite sequence of states. The cumulative reward on an infinite sequence of states is the summation of rewards at each of those states. Right? Summation at each of the states. Why should an infinite summation be finite? Most likely it will be infinite. If it's infinite, then everything is infinite. If everything is infinite, there is no better versus worse policy. So the problem becomes degenerate. Do you see this? Okay? So this is the immediate problem. Why should value iteration converge at all? Sum of rewards of an infinitely long sequence is likely to be infinite. You need to stop it from being infinite. When was the last time you thought of a sum of infinite series of numbers and tried to sum them up and found that they're finite? Anybody remember geometric series? The calculus? Right? If you have a geometric series with a common ratio r strictly less than 1, then you are guaranteed that that infinite series will sum to a finite number. It's a convergent series. Okay? So, I have the following situation. RS0 plus RS1 plus RS2 plus RS3 plus RS infinity. These are real numbers. They're just real numbers. I want this sum somehow to become finite. What will I do? I'll say, take a beta less than 1, strictly less than 1. A positive value is beta, strictly less than 1. And then just throw this here. Beta power 0, this. Beta power 1, this. Beta power 2, this. Beta power 3, this. You see what I'm saying? If you do this, among all these R values, let's say R max is the maximum reward that you can ever get in any of the states in the world. So that means you don't know all these numbers, but all of them have to be less than or equal to R max. Then what I can do is I can take R max out and subtract everything by, divide everything by R max. At this point, you should be able to see this series is actually less than just the series beta plus beta square plus beta power 0, which is 1, plus beta square plus beta cube, etc., beta power infinity. Which, how many people remember what is the sum of that? What's the sum of the infinite series? 1 plus beta square plus beta cube, etc. 1 by 1 minus beta. You never thought you'd see this again. Your life works because of this. Okay? So then you know that it's whatever this sum is, it's less than, the sum of this is less than R max by 1 minus beta. Magic! I reward shape such that the rewards will add up to a finite number. At this point I'm done, because I already have a working code. I just have to make it instead of just basically taking this and adding it to RS4, I just put a beta and add it. You see what I'm saying? So I just need to take this and say RS4 plus beta times this whole. You do this, you're guaranteed that stuff will work. Stuff will work and numbers will come out. That's all anybody ever wanted. Question is, what the heck did we do? Why is this reasonable?